6.3, sampling, distributions, and estimators. We're now considering the concept of sampling distribution of a statistic. Instead of working with values from the original population, we want to focus on the values of statistics, such as sample proportions or sample means obtained from the population. Okay, so we're talking about a sample, we're talking about a distribution, we're talking about population. All of those things are things that we've talked about before. General behavior of sampling distributions. When samples of the same size are taken from the same population, the following two properties apply. Sample proportions tend to be normally distributed. So remember, when we're talking about a normal distribution, we're talking about that bell-shaped curve. That's how the numbers are spread out, I guess. All right, so it's kind of important that we take samples of the same size, but it says sample proportions are normally distributed. And so proportions, you got to think about what a proportion is. Proportion is like how many are there out of the total. Okay, it's kind of like part over total. It's kind of like, I don't want to say it's probability because it's not, but we calculate it the same way. It's a fraction. What fraction of the total are we looking at? Proportion. The mean of sample proportions is the same as the population mean. Okay, so we're talking about the mean of the sample proportions. It's the same as the population mean. So well, we're not there yet. Okay. So we get to this slide and it has a lot of information and it just kind of tries to summarize the main ideas of the entire lesson. Get a couple of symbols that you may not be familiar with. The symbol for proportion is called p hat. That's how you say it, is p hat with that little symbol over top of it, p hat. But it's talking about the proportions. And kind of the main takeaway here is sample proportions tend to have a normal distribution. When we look at means, all right, you've got this symbol that's talking about the sample, and you had this symbol that was talking about the population. So some of the symbology gets a little bit difficult, but understand that there's a difference between a sample and the population, and sometimes those numbers are calculated differently. Sample means have a normal distribution. Hardest one, I think, to think about is when we talk about variance. The sample variance has this symbol and the population variance has this symbol. They're calculated in different ways, but this time it's not a normal distribution. This time the distribution is skewed, and we would say that's skewed right. That seems ironic. You might think it's the other way, but think about the longer tail is on the right side. That's skewed right. The sampling distribution of a statistic, such as sample proportion or sample mean, is the distribution of all values of the statistic when all possible samples of the same size n are taken from the same population. The sampling distribution of a statistic is typically represented as a probability distribution in the format of a histogram, formula, or table. All right, so anytime you get to something that you don't understand, you better read it again. Maybe you have to read it 3, 4, 5 times, but try to read this enough times to where you understand what they're talking about. All right, essentially, it's just saying we're going to have a distribution. It doesn't really say it's normal, but that's what we're probably going to be looking at. Sampling distribution of the sample proportion. Sampling distribution of the sample proportion is the distribution of sample proportions or the distribution of the variable p hat. With all samples having the same sample size n taken from the same population, the sampling distribution of the sample proportion is typically represented. Okay, there's a distribution, histogram, formula, table. All right, so population proportion, sample proportion, p hat. And again, if you don't know what a proportion is, it's like part of the whole thing. behavior of sample proportions. The distribution of sample proportions tend to approximate a normal distribution. Okay, got that. Sample proportions target the value of the population proportion in the sense that the mean of all the sample proportions p hat is equal to the population proportion p. All right, so basically what they're saying is the mean of all the sample proportions equals the mean of the population, okay, the population proportion. And so that's good. We take a sample, we take a bunch of samples, all those samples have to be the same size. The average or the mean of those samples is going to be the same, sample proportions is the same as the overall population proportion. Okay, so write that down. Example 1. Consider repeating this process. We're going to roll a die 5 times and find the proportion of odd numbers 1, 3, or 5. What do we know about the behavior of all sample proportions that are generated as this process continues indefinitely? Okay, so think about it. If we roll a single die, those are our possible outcomes. And so they're talking about the proportion of odd numbers. Well, here are the odd numbers, 1, 3, and 5. And so don't think about this too hard. The proportion of odd numbers is 3 out of 6, or 0.5. Okay. And so we're talking about the population. If I, did this 1,000,000 times, I would expect 500,000 odd numbers to come up. All right, and that makes sense. That's our population right there. That's kind of our expected value, our ideal value. But it's really hard to understand this, I think, without really seeing some numbers. And so that's why I'm going to show you a spreadsheet here. So I made this spreadsheet, and what I've got here is I'm rolling a die 1, 2, 3, 4, 5 right there. So this right here would indicate one iteration of this experiment, right? You're rolling a die 5 times, okay? So for example 1, we're talking about odd number results. If I look at, and we got all this stuff over here, but if I look at this, okay, think about how many odd numbers you see. I see an odd number here and here. That's 2 odd numbers, okay, out of the 5 rolls. So the proportion is basically 2 out of 5. That's all I'm doing, part over total. 2 odd numbers out of 5 total numbers, 2 out of 5, that proportion is 0.4. So I went ahead and rolled these die basically 1,000 times. You scroll all the way down there, that's 1,000, okay? There's 1,000 rolls, and I found there's 2 odd numbers here, there's 1 odd number here. So I found all these proportions. I did it 1,000 times. And so the possible things you could have 0 odd numbers, 1 odd number, 2, 3, 4, 5. And I had my spreadsheet count up the number of times I had 0 odd numbers, 1, 2, 3, 4, and 5. Likewise, your proportions, the possible things you could get are 0 fifths, 1/5, 2/5, 3/5, 4/5, 5/5. Those are the possible proportions, but it's the same number. So it doesn't really matter if you look at the odd results or the proportions, you're getting the same numbers. So I graphed those results. I made a chart out of these numbers, and it looks like this chart. And you're supposed to notice a couple of things, all right? The first thing you should notice is that this is basically a normal distribution, right? This looks like that bell-shaped curve, right? And I can change my numbers. If I change my numbers, recalculate, it'll change slightly, but it still should be a bell-shaped distribution, all right? So the first thing I want you to do is I want you to kind of copy this sketch over again. There we go. So just kind of do a quick sketch of it, and make sure you've got 1, 2, 3, 4, 5, 6 bars. I know the x-axis isn't labeled, but think about what those x-axes could be. If we're talking about proportions, it's going to be 0, 0.2, 0.4, 0.6, 0.8, and 1. So we can, I guess we could type those in. Okay, doesn't have to be super awesome. This scale goes up to 400 by 100s, and just notice that the middle numbers are right around 300. It doesn't have to be perfect, because if I redo the experiment, they're going to change anyway. It should be a bell-shaped curve, though, a normal distribution. And so that's something you're supposed to notice, is that this is a normal distribution. Okay, so write that down. This is a normal distribution. Now, what you can notice, and you can see it maybe better in the spreadsheet over here, but most of the numbers are kind of in the middle here, basically in between 0.4 and 0.6. Okay, and that's what we would expect. Earlier, we found that that the proportion was supposed to be 0.5, right? 3 out of 6 was 0.5. And that's exactly what this says. Most of these numbers are going to be around 0.5. That kind of hints that the mean is 0.5. So that's what I did right here. I calculated the mean of the sample proportions. So what I did is I just took all of these numbers right here in this whole column. I found the average. I found the average of these numbers. The mean of these numbers was basically 0.5. All right. So I want you to, mean of sample proportions. Write that down. Mean of sample proportions is about 0.5. And that's kind of our main takeaway. The mean of P, I'm going to put a hat over that, equals mean of P. Okay. The mean of P hat is the mean of the P, or the mean of the sample proportions equals the overall mean of the P. That's kind of our takeaway. All right, so let's move on. Sampling distribution of the sample mean. Now we're talking about means, and it pretty much says the same thing. The sampling distribution of the sample mean is the distribution of all possible sample means. Notice this symbol again. With all samples having the same sample size n taken from the same population. Okay. Behavior of sample means. Distribution of sample means tends to be a normal distribution. Okay, fine, we got that. Sample means target the value of the population mean. That is, the mean of the sample means is equal to the population mean. So we're talking about the sample means is supposed to equal mu. Okay, that's what's supposed to happen. So example 2 is that same exact problem, right? We're still rolling the die 5 times. So if we roll this die 5 times, this time we want to talk about the mean. So example 2, I take each of these rolls and I'm going to find each of these means. I'm going to do that 1,000 times, okay? I guess before we do that though, think about it. I could roll a 1, a 2, a 3, a 4, a 5, or a 6. Think about what the mean of that is. Okay, if I add that up, that's 3, 6, 10, 15, 21. That's 21 over 6, which is 3.5. That's the population mean. That's mu. Okay, I know that the mean of those rolls would be 3.5. All right, if I did this thing, you know, a billion times, that the average is going to be 3.5, the population mean. But we don't want to have to deal with a billion numbers, so we take samples. That's what we're doing. Okay, so that's what we've done here. We roll this 5 times, find the mean. We roll 5 more times, find the mean, and so on, 1,000 times. So I did this 1,000 times, and I determined that the means could possibly be these values. All right, from anywhere from 1 to 6 were the possible values. And so I took my spreadsheet and I looked for those possible values and I counted up how many times those values showed up, and I graphed it over here. This is the graph. And again, you notice we pretty much have this normal distribution, this bell curve. Okay, and it's not perfect. It's not perfect. The more we did this, if we did this a billion times, it would look pretty much perfect, but we only did it 1,000 times. If I change my numbers, I could recalculate, and it should change, but it's still basically a bell-shaped curve. So copy that picture over. And again, it doesn't really have to be perfect. I don't mind if it's not perfect. I need a make sure it's a normal curve. Make sure it's normally distributed. Say what? Going up by 50? The vertical axis is going up by 25, but I don't even know if I would pay attention to that. Just draw a bunch of bars, make sure it's normally distributed. I don't even think you need to have the same number. Just we've got this normal distribution, and we know this. All right. What do we know about the behavior of all sample means that are generated as this process continues? Definitely. The question is, what do we know? Well, we know it's normally distributed. Okay. But more than that, we can talk about the means of these numbers. So if we look at these means, we see how the most of them are right here in the middle. Okay, well, specifically, you look for the biggest numbers, and those biggest numbers are right here in the middle. So you would expect this average to be 3.5, right? And that's what we want. That's what it said before. Our population mean was 3.5. It looks like all these numbers are going to be in the middle here, right in between. You know, look at the two highest numbers are 3.4 and 3.6. So we're going to be right in between 3.4 and 3.6. Okay, so what I did was I found the means. Okay, I found the average of all these means. So I took this whole column and found the average of this column, and lo and behold, I got basically 3.5. Right? That's kind of your takeaway. We're looking at sample means is about 3.5. Okay, sure enough. So x bar equals mu. The means of all of those sample means equals the population mean. Okay. Now we talk about variance, and I think variance is the hardest one to understand. We just don't have a very good visualization for variance. But remember, when we talk about variance, when we talk about standard deviation, we're talking about how much the numbers are different than the mean. Okay. I've used the example a few times. If I listed out everybody's age in this room, I'd see a lot of 17s and 18s. The standard deviation would be pretty close to 0 because those numbers don't deviate very much. All right, we're talking about how much those numbers vary from one another. All right. So this says the sampling distribution of the sample variance is the distribution of sample variances. Notice you've got S squared this time, with all samples having the same sample size n taken from the same population. So here's a reminder of a couple of different formulas that we've seen before. Population standard deviation and population variance. We might have to use that if we had to calculate something by hand. Since I'm doing it on spreadsheet, I don't really need any of that, but you might need that later for your homework. Behavior of sample variances. The distribution of sample variances tend to be distributions skewed to the right. All right, so notice that. This is not normal, skewed to the right. Remember what that looks like. It's like, and has a long tail, right? The sample variances target the value of the population variance. That is, the mean of the sample variances is the population variance. So we're saying this. Okay. So here's number 3. Number 3, consider repeating the process, still rolling the die, and we're talking about the variance this time. What do we know about the behavior of all sample variances that are generated as this process continues indefinitely? I think it's a lot harder to think about the numbers with variance because it's harder to understand. So I'm doing the same thing. I'm rolling this die 5 times, and I repeat that 1,000 times. And I calculate the variance, or how much these numbers vary from one another. Okay. So notice the lower the variance, the more these numbers are the same. I wonder if I could find one that's, yeah, here's one that's really close to 0. So these numbers don't vary very much. If I could find one that equals 0. Hard to find one that's specifically what you're looking for. It looks like there is one. But the possible values that the variance could be are anything from 0 to 6. I looked through this whole list of my sample variances, and I know that we can have numbers between 0 and 6, so I counted them up. That's what this frequency does. It counts them up. And I think this one's hard to see once you count them up. It's hard to tell that this is skewed right, but this is supposed to be skewed right. I think with the rounding, and I mean, you look at this formula, these numbers are going to be pretty nasty, I think. All right. And so there's rounding involved with this spreadsheet. The numbers just don't look great. All right. But we know it's going to be skewed. So this question said, what do we know about the behavior of the sample variances? We know it's going to be skewed. Okay, we know it's going to be skewed right. So I want you to let's just draw one that's skewed right. So that's terrible. Looks something like that. Okay, it shouldn't be symmetrical. It's going to have a right tail, and you're going to say this one is skewed right. All right, so what else do we know? Well, we look at the numbers. And so what I want to do is I want to calculate the population variance, and the population variance is basically the variance of all of the numbers. Remember, the difference between population and sample, population is everything, sample is just some of the numbers, right? So population, what I did was I calculated, I like grabbed everything right here, okay? Like everything all the way down to row 1001. And I calculated the population, that's what this P stands for, the population variance from A2, which was this cell, down to cell E1001. So I grabbed all of these red numbers right here, and calculated the variance of the entire population of my numbers here. And then that's 2.8 or so. And then the mean of the sample variance, I found the average of this column again, like I had been doing in the previous examples, but I found the average of all of these numbers. And you notice that they're pretty much the same, right? The only reason they're not exactly the same is because I would need to do more numbers. The higher, the more numbers you do, if I did 1,000,000 or 1,000,000,000, I would expect these numbers to be even closer. The more and more and more you do, the more ideal your numbers become. But this is exactly our conclusion that we're drawing here, is the means of the sample variance equals the population variance. The mean of the sample variance equals the population variance. Now we have an estimator. An estimator is a statistic used to infer or estimate the value of a population parameter. Okay, so remember, when they're talking about a statistic, I'm talking about the sample. Way back, I believe it was chapter 1 or 2, you had this this mnemonic device that said sample, statistic, population, parameter. And the point of that was just to tell you, when they say statistic, they're talking about a sample, all right? And when they say parameter, they're talking about the population. An unbiased estimator is a statistic that targets the value of the corresponding population parameter in the sense that the sampling distribution of the statistic has a mean that is equal to the corresponding population parameter, okay? I guess what this would be useful for is if you've got a whole bunch of numbers, okay? If you've got 1 billion numbers and you don't want to have to deal with 1 billion numbers, you deal with smaller samples, okay? So unbiased estimators, it's saying proportion and mean and variance of your sample, your sample variance, your sample proportion, your sample means are going to be good estimates of the population. That's unbiased. Biased is the opposite. Biased estimator does not target the value of the corresponding population parameter. So median, range, standard deviation, that kind of deal, all right? Why sample with replacement? Sampling is conducted with replacement for these two very important reasons. When selecting a relatively small sample from a large population, it makes no significant difference whether we sample with replacement or without replacement. To me, that reads like a contradiction. It seems like that statement completely contradicts above. So I guess they're saying if it doesn't matter, if it makes no significant difference and it doesn't matter, we might as well, in my opinion, because of the second one. Sampling with replacement results in independent events that are unaffected by previous outcomes, and independent events are easier to analyze and result in simpler calculation. We like independent events. So I think this one seems more important than the other one. But anyway, why sample with replacement? There you go, that's why.